This morning I will be talking about more practical things. Are we sharing? So I actually wanted to, before I start my line with modeling, I want to say some basic things that are very important as you know. It was not the mathematicians that started the first. In terms of application, modeling started with the need of public health. Then the public health doctor who is a physician. There have been some, when I mean modeling application, before that time there have been some modeling that are theoretical, like Daniel Finally, and then afterwards it came to people like McHenry and McHenry. So now the first person that started working on a more practical aspect of modeling was Ross. So Ross said something, I will quote it: as a matter of fact, all epidemiology concerned, as it is with the variation of disease from time to time or from place to place, must be considered mathematically. However, many variables are implicated. It is to be considered scientifically at all. So, to say that the disease depends upon certain factors is not to say much. Now, in epidemiology, what they do is that disease depends on certain factors, and then they look at those factors, collect data on those factors. Like, take for instance, for lung cancer, the risk factor for lung cancer is smoking. So they collect data on people who are smoking, do the descriptive analysis, and then that's all. I mean, that is the best people do. Now, and then, so that was why the guy said, to say that the disease depends upon certain factors, it's not the same one. For malaria, what's the real risk factor for malaria? Risk factor for malaria? That's number one. You understand? An environment can be dirty, but there are no mosquitoes.
That's true.
Are you getting what I'm saying? There are places in the world. I mean, when I mean mosquitoes, for the Anopheles mosquito, not just any mosquito. Anopheles Anopheles mosquito. There are places in the world where we have mosquitoes. I was in France some few weeks ago. I took the mosquito, I now put it on my in my room. I sent it to the bathroom plumber. So there's mosquito in France, but they are not carrying Plasmodium falciparum malaria. There are mosquitoes everywhere, but they may not carry the parasite. Are you getting it now? So for each disease there is a risk factor. Are you getting it now? So the public health officials, they focus on the risk factor, and then they collect data on, like when COVID came, they were after the risk factor. They could not do more than that. So modeling did beyond the risk factor, looking at what the risk factor depends on all that. So until we also form an estimate as to how large each factor influences the whole result. How does this risk factor, in terms of what is the estimate of mosquito, like mosquito that is causing this stuff, how does it affect the whole stock? That's when modeling comes in. So how likely does each factor influence the whole result? And then the mathematical model of treatment is really nothing but the application of careful reasoning to the problem and issue. Now, it is one thing to be using mathematical model, and then you are using it theoretically. There is no careful reasoning. Now, the mathematical model needed to assist the public health official is mathematical model that is dependent on reasoning outside the box. You have all the theorems, but do you know which one to apply to get something that will be needed, the needed thing for people you are working with? Are you getting that? So I think that was what Ross came about, and he became the father of modern mathematical epidemiology. I used to say something that Now, as I go through the journey of learning mathematical epidemiology, one of the first things I did is to trace people who are the forefathers, the core players in that war, because that will guide you on where the whole story started from, and then it will also guide the kind of research you do. You understand? So there are people who have started this stuff, and then it becomes a continuum until today. So I would like to quickly look at some few things about. They have dealt with some of these things yesterday, but I still feel that I should say some few things about them. What is mathematical modeling? Now, mathematical modeling is an abstract representation of a system based on mathematical terms in order to study the effects of different components and consequently to make predictions. So you have a particular system. Now, the system does not necessarily be biological. It could be a chemical system. It could be, it may not, the one we are dealing with is epidemiological, but some systems may not be that. It could be, I have somebody here who is interested in crop, agricultural system, economic system, and all that. But one thing is that what we are doing at the end of the day is not to complicate, because the real world is already complex. Now, we are bringing a model to simplify, not to complicate. Now, any model you build that is even more complex than the real world will not be useful. What I mean is that it's not as if model will not be complex when we want to attract real world, but it must not be as complex, even more complex than the real world you are looking at. Because as you go on, if you are going to track a model that can speak to the real world, it must be models that are complex but also simple. And that's why we are going to talk about the principle of parsimony. Not so simple, but not so simple, just like Albert Einstein said. They're not so simple. So you have to, there's a trade-off between the two. Now, we said it's an abstract representation of a system that is based on mathematical terms in order to study the effect of different components. And then the development of models depends on several factors such as data, you have the data at hand, and the hypothesis to be addressed, and the experience of the modeler. One of the things I've found out in Nigerian modelers is you read the paper and you don't know, okay, what is the objective of this paper? What is the aim of this paper? Everybody just say, we want to find global stability, the lab functions, and then we try to find out what when is less than one, and how when is greater than one, and then at the end of the day, we realize that the result was available to numerical simulation to stop. And then the paper is published. But at the end of the day, it's published but it's useless. Because nobody uses the work. You are happy that you are published, fine. But the fact remains that we need to move beyond that. It's a good level, but we must not continue there. Any research is a progressive thing. Any research you are doing that is making you to be circular, then you cannot advance. You are just rotating on a particular thing for 10 years or 20 years of your research work. Just on one thing, you didn't advance. That's not the research. That's why they call it research. Research, then read. It means that there must be continuity, there must be progression. If you are not progressing in research, then it means that, your research cannot affect large number of people, global world. So and that's one of the reasons why we are here. We learn new things, and then you go back and start saying, okay, how do I improve on what I've been doing before to get better? Are you getting now? So that's the idea. So the development of mathematical models depends on several factors. The data and the hypothesis to be addressed and the experience of the modeler. And these three factors can play a lot of role. Now sometimes as a modeler you do not have data. It's possible. Maybe when the disease has just started, you want to project it to what you have. Like Rabi also said yesterday, You want to see what's going to happen. You try to put in vaccination and see the trend and all of that. Yeah, you can do that. But you cannot do that for life. You know, when you already have the data, the expectation is that you should test your model with your data to see what has been going, what is going on presently. Now, another issue about modeling is that it's also location specific. Now, the dynamics of malaria in Ekiti State is completely different from Kwara State. Cannot generalize. Malaria may be going on in Kwara. Now, the control you will need to capture Kwara may not be the same as even the one you use in Kogi that is very close to Kwara. The reason is because when you talk about the topography of that place, and then the climatic variability there, the environmental factors like land use and all of that, they play a lot of roles. Then the environmental systems. Now, take for instance, there are some states that they do a lot of environmental sanitation. Are you getting that? They could be nearby states. So the kind of method of control intervention you will use in certain states may be different from the other states. So you also have to think about what goes on in that environment you are working. And that is why people conduct experiments in Nigeria. The same experiment you conducted here, you may not get the same results if you go to UK. You know why? The temperature, the climate variability of that place change is different from here. So when the person say, I want to conduct this kind of experiment here, it will be very results. So now, when you are developing modeling, you have the data, that is good. You have to understand your data and what your data is saying. And then on that, you are able to build an hypothesis. What are the questions you want to answer? At a time, you cannot answer all the questions in the world. There must be a particular question you have seen from the hypothesis, from the data that you want to look at and that you want to study. Right? And then the experience, that's another aspect. Now, the more experience you are in modeling, the better. You understand? Let me give you an instance. So, you are seated, right? Now, you are seated. You are seated, and then it has made you to be short, right? You are short because you are seated. Now, it means that you cannot see very far. Now, if you turn your chair down and then you want to look at that place, because I'm standing, I'm taller, I can see ahead. So what you are writing there, and see that this thing you are writing, they don't fit. And that's what they call experience. Now you need, as you go on in the modeling, you need to gain experience. It will also help you to better your models. So the shorter you are, then the lesser productive will be your modeling expertise. So as you gain experience, then you go to learn, and then it changes your size. Your height changes your size. Understand? So that is when once model parameters are fitted with experimental data. Now sometimes it will also be an epidemiological data. So with experimental data or the epidemiological data, models have the capacity to serve as virtual clinical trials to uncover the success and pitfall of treatments as well as vaccine. Now, mathematical model can be fitted, and that's one of the things we'll be using how to do in this session. Now, we fit model with data and try to see some data we have gotten and see how we behave with the data. In fact, we can also, apart from fitting, we can use it to predict. Like you see in the data, some of the data we have, we'll fit some, and then we will also see how I was able to fit it to, predict, use it to predict an hepatitis data from the UK. And the hepatitis data was from 2014 to 2015. We wanted to see what will happen from 2015 to 2017. can see that. And then you can see more than that. You know, there are levels of prediction. We have forecasting. Forecasting may just be within 2 years. We have prediction. Prediction is within 10 years. And then we have projection, which is more than 10 years. You can use modeling to do that. Now, so models have the capacity to serve as virtual clinical trials. That was what I was saying. We were saying the other time. You put the vaccination in your model. They are not yet vaccinating. But you can try it. You can conduct a trial. So you said, what will be the effect with vaccination? What will be the effect without vaccination? So without vaccination, you become like a placebo. Some of you are doing experiment. You know, you have a placebo. The one you didn't put a vaccine or treatment on, and then you have the one that you are conducting stuff, and then you measure. You look at it, you find and then have the capacity to serve as virtual clinical trial to uncover the success and pitfall of treatment and is yet to be dispersed. Sorry. Now, modeling. Why do we model? You want to plan for outbreaks. There is need to plan for outbreaks. Now, there is an outbreak, or before the outbreak, or when the outbreak is on. In NCDC, they have a group that is called REDISE. REDISE is a unit that is meant for planning for outbreaks, planning for emerging disease. So they usually use modeling a lot. At one time, I had done a project for them. They call it vulnerability. That's VRAM, vulnerability risk assessment mapping model. We did a project for them on developing a model to capture about 11 NASA in Nigeria, and then they prepare for outbreak. And in what way? We want to see how many health facilities do they need to capture for the next outbreak. Maybe like a monkeypox. You want to see what are the treatments or drug or anything they have on ground for this particular Lassa fever against the next outbreak. And then what we have, can those things we have on ground, will they be able to cater for any outbreak that occur later in life or maybe in the years to come? Because there are some diseases that are epidemic prone. You understand? Like, take for instance, diphtheria. Diphtheria happened this year, and then it's almost like every year thing. Lassa fever is also like that. It's an epidemic prone disease. It comes every year. Now, as of December now, from December, January, you see this kind of thing coming up in Nigeria. Now, what is the spread of what is the speed of the spread? You know, when there is an epidemic, there is going to be something like the velocity type graph stuff. Now, this is the infection, and then everything is with respect to time. The disease started like this. That's great. Now, we don't know when this disease will reach its peak. So the fear is that when are we going to get to the peak of this infection? Now, at this point, usually is when we can calculate our outcomes for that particular location or that country. We can't calculate outcomes when the disease has started dropping, because something has happened. When the disease starts dropping, it means that there is an introduction of an intervention, or maybe people have started recovering, either by natural immunity or by anything. And at that time, you have to calculate how the presence of susceptible and non-susceptible population. So at this point, it's only a susceptible population. I know it's increasing, and then it will have a steady state like this, just like your physics. Now, the epidemic curve is just like a velocity type graph. So, and then it started dropping at a particular time. Started dropping. In stochastic, we talk about in a normal differential equation. Now, in this workshop, we are not dealing with stochastic aspect. But we are going to take that part because that's part of the thing we do here. We deal with the aspect of stochastic models. Now, in stochastic, we talk about time to extinction, the probability of extinction of a particular disease. Now, for that, at what time does the disease start dropping? You understand? So then we talk about this. The disease started dropping, coming down. So at this time, maybe introduction of many things. Maybe like non-pharmaceutical interventions, or some drugs, some treatments, some it's malaria. Like now, Nigeria has been interventions that have been put up for malaria. And then, as at now, we cannot calculate how much. We can only get how many. But if you have data that shows what happened before, that is before 2000. Because from 2000, Nigeria started serious things on malaria. And that was when they started their national malaria strategic plan. So they are running the 5th plan now, which runs from 2021 to 2025. Now, if we are going to look at that, it means that we have to look at control interventions that have been put in place. Then we can calculate effective reproduction number, which contains both susceptible and non-susceptible population. Now, why we model severity? How severe is the disease? There are some diseases that, like they are very severe to the point that they don't waste time to go through this place, to go through this pattern. Expose, they move straight here. You quickly become infected and infectious. There are diseases like that. So you look at the severity of the disease and then the intervention effectiveness. Now, you can spend money on the intervention, and then it doesn't give any result. And that's why it's a very big problem of choice. Because now, there are donors who are giving that stuff, and then they don't want to continue. It was in Nigeria ahead that HIV was in Nigeria. I mean, some people were collecting funding, and the funding did not end because the same problem continues every year. Why? Because they are enjoying the money. Now, the issue of intervention is a very serious thing, because it's like if you are spending your money, we are not spending it rightly. You are spending your money to deploy control intervention to a particular place, but the money you are spending, you are not getting results. You understand? You are not getting results. So there is need for techniques to know how to deploy a particular intervention that will be effective for this particular place. So that at the end of the day, you know that when you give this intervention here, it brings about results of what you need. So you don't continue to waste your money. So that is why modeling is needed in determining the optimal intervention, effectiveness of optimal intervention. So you can use model to determine how effective, what are the combinations of interventions that will be effective, and use it. Or you can use model to predict. Like in this place, if you combine this and this together, this is going to work. Like I said, all these are very things, they vary, and some will be also. They could also lead to some stochasticity. It depends on the environment you are deploying the intervention to. So, what kind of model do I need? Now, the kind of model you need depends on the question that you want to answer. And the question you want to answer depends on the kind of data that you have at hand. Are you getting what I'm saying now? Now, it also depends on likely on the biology, yes, the biology of the disease. Now, because if you don't know the biology of the disease, what do you want to go there? You don't know the biology of malaria. Just saw a paper on malaria. You saw SIR, and then you pick it, started writing. You just change maybe they say SCIR. You say, okay, me, I'm not considering E, I will use SIR. It is stupid. So the first thing to do, go and look at Lassa fever. What is the biology of Lassa fever? We advise people here that if you are doing a model in Lassa fever, go and go back to the biology. Sit down with the biology, get the biology. When you get the biology, then you will be able to understand how to model. So that means you go to PubMed, check PubMed, and look at papers on biology. When you understand the biology, you will be able to write your own model in your own way to address your own problem. So you cannot model, do a new model or do a new work using somebody else's modeling paper. No, cannot. You need to check some biology of material literatures. So for those kind of model we have, you look at them, statistical, dynamical, or mathematical, health and performance model. Now, what are statistical models? Statistical models are data driven. They are not the same exactly as something they are not the same as mathematical models. Now, they are data driven. Now, if you don't have the data, don't actually venture into statistical models. Especially, you are not in the aspect of mathematical statistics, where you are doing the differential and all that. But if you want to use it to model a particular scenario, you need the data. They are data driven. And then they explore correlation and understand the trends. When you share, so we explore correlation, understand the trends and patterns of data, regressions, time series analysis. So some of the things. Last week we were looking at the data from Lagos State, and then the data was for malaria from 2013 to 2014 to 2023 June. So and then we wanted to see, okay, what we can use, what can we do with this data? So we subject it to the time series analysis. That's I think we use animal as autoregressive. So moving average, and then we're able to forecast what will happen between 2003 and 2005. We have the data, we have the prediction, we are writing something on that paper now. Now it was for Lagos State, and then we forecasted between 2003 June till 2025 what is going to happen in that state. Okay. So we can use statistical data if there is models, if there are data. And then they will not only show us the correlation, they will also help us to understand the trends and the patterns. And not only that, some of them can also quantify. Like the wavelength analysis now, you can use it to quantify. You want to quantify the correlation between two distances, you can do that. And then they are used for nowcasting and forecasting to predict the current epidemiology and where it might be in the next few weeks. So we can do that with statistical models. They can also be used to estimate the efficacy and effectiveness of current treatment and prevention measures. And then we look at dynamic models. So dynamic model uses mathematical language to describe the underlying biological and behavioral drivers of disease transmission. So you use mathematics, and then the mathematical models, once validated against historical data, can be used as tools for scenario analysis. What do you mean by that? Now, if you develop a mathematical model, you can use it to, just like I said the other time, you set the model, you have the model, and then you put in some control measures. And then there are two ways to put control measures. One can be control measures that are constant, and the other one can be time dependent. Now, for constant control measure, you can build a scenario analysis in the sense that I set my treatment to 0, I saw what happened, and then I put my treatment there, not set to 0, and I'm able to see the way the graph is changing. That is what we call scenario analysis. And then scenario analysis provide evidence to support policy making, allow the exploration and comprehensive of options for intervention against a disease to support decision aimed at controlling that disease. So we have dynamic models. Now for dynamic models, you can simulate the process. And then in the dynamic model, we have the deterministic. The deterministic, there is no randomness involved. There is no randomness involved. It is static. And that was why you see that if you are plotting a deterministic model, you plot for the effective class. You understand? The effective class may be growing like this for deterministic model. You understand? In deterministic model, everything is predetermined. So you have it like this. But for stochastic models, which explore outcomes and obtain distribution of the outcomes, that means for every outcome you have, there is a probability distribution attached that you have to understand. Now, this one you can run simulation for 100. So you are getting within a particular time for a particular within 5 days. Within 5 days of an occurrence of an epidemic, and you run a stochastic simulation on it, it can give you 100 different simulations within a particular interval. And that's a very good one for us, because you'll be able to see that, okay, within this particular interval, we have this number of cases, between 5 to 50 cases of disease. The deterministic give you 5, but the stochastic give you between 5 to what? To 50. That's the difference. So now in our subsequent workshop, we have just started. We are moving into different levels. We have to start from the basic, and then we move to other steps, how to explore other kinds of models. So we have, then you obtain, in this one there is randomness. Randomness is very important. The noise, the variability, the stochastic fluctuations are there in the data, and then you have to capture them. Some of those parameters also link to some stochastic fluctuations. Take for instance humidity. Humidity in your body is different from humidity in the person sitting beside you. It's a very thing. Humidity in a particular state is different from another state. The level of humidity to a particular is natural humidity. So it's something that is stochastic. So, and then we have the metapopulation and network. And on the metapopulation we deal with mobility, disease mobility, and then individual or agent-based models. And then we have the district models, use whole numbers, rates converted to probabilities, possibility of disease eradication. And then for stochastic model, you can see what I was saying the other time. The number of infected, this is the x-axis, and then 0 to 5. You see that between 0 to 5 days, look at the number of people. Between 0 and 50 people have been infected. So this simulation is run like 100 times. So you find out that it's just on a number of infected. So you find out that the number of people between, if you look at between 15 days, 0 to 15 days, if you look at it, you trace it up, the number of people that will have been infected. So metapopulation. The concept of metapopulation does not originate from epidemiology, but in ecology. So a metapopulation is a group of population of the same species that live in spatially isolated area but interact on some level. Now you are living in Ilorin, but you are working in Ekiti State. Mosquito bite you in Ilorin. You went to work in Kogi, and then you fell down in Kogi. They took you to the hospital in Kogi. Now, but where is the source? The source of that infection is where? Ilorin. So that's why we introduce special temporal into models, because like people are moving, mobility is there. You are moving from one place, commuting. It's either you commute temporarily, you migrate to a place temporarily, or you migrate fully. You are there fully, especially during this what's it called? People, no, not festive period is there. Yes, during festive period, you see that people come back. When you go to your child's school, when they resume, take for instance during December now, people will go and travel from one place to the other. When they resume, go and take records. There are schools that you find some outbreaks, primary school, because children easily, as you are sitting here now, the contact rate is very low. If there are children there, the contact is very high, because children will put their hands in their nose and everything, and then the disease is spreading. Some have gone to Zamfara for their ordain, they came back. Some have gone to special locations. So we use this to capture disease at the special level. So disease is not just a function of time, it's also a function of location. Disease spread. So these are, we want to talk about special stuff, we make use of better population models. So this occur when different populations live in fragmented habitats, and then but are connected through migration. And then epidemic models consist of metapopulation models, consist of end patches. You have patches in a place and then another place, and then they commute with each other. The population of each patch is assumed to be homogeneously mixed. Actually, you can use an SIR to capture this, but it's going to be SIR with location. You know, I may have like, maybe I'm going to consider Ondo State and Ekiti State. So for malaria, I have Ekiti, S-E-I-E, and then Ondo, I have S-O, maybe S-N-I-N-R-N. So there is something that brings these people here, and then this one also goes there, location. And then if you have the data for that, there are a lot of things you can do with that. So you have a large number of systems, and you are seeing how people are commuting from one place to another. Now it is divided into typical epidemiological classes, susceptible, effective, and other classes. The network model, it tracked the network of contact between individuals. When there was COVID, there was what we call contact tracing. Now contact tracing is not an intervention itself, but it's what they use to track interventions, other interventions, to better them. There is a disease, and then somebody has contacted, a successful person has contacted an infected person somewhere. Just like when the Italian guy came to Nigeria on February 28, 2020, where he was. And we began to trace how many people were in the plane with him. And then who had attended to him, we trace those people. And then it's a network. So infection can only occur between infected individual and a subset of the population with which they are in contact. So then we have the individual based or agent based models. This track what happens to each individual in the population. Allow chance to determine whether or not they become infected and infections are dispensed them. Each agent or important group assigned a compartment. So the number of compartments can increase exponentially for an agent-based model. And for this you need a supercomputer to run this. And each agent has a set of attributes, each devastation status, rules are set for how agents interact. You have health economic models. You have health economic, I use primarily to explore the potential cost and benefit of health interventions. You know, so these and that aspect, and then statistical models look at their complexities. Now you start from the simplest and the univariate linear, and then you move to multivariate linear, generalized linear, and generalized linear and mixed model. Now you see from my graph here, there is an increasing realism as they go down, because they are becoming more complex as they go down. But as they become more complex, it's difficult to track. Their tractability becomes more complex. So it decreases in tractability as they go down. Now, you also have like for dynamic models, we started from the deterministic model, which can be continuous or discrete, and then we move to stochastic models, then we move to beta population and network model, and then we move to agent-based. Now, most of these are time dependent, like the deterministic model will be time dependent, and a lot of things can also be done there. Now, but you find out that there is increasing complexity and realism as you go down. Increasing complexity and realism, it becomes more real, the model tends to more realistic features, but it becomes more complex. And also it decreases in tractability as they go down. Now, how good is my model? A model should be parsimonious, yes, realistic. Should be as simple as possible, but not so simple. That is parsimony. Then conform to data. A good model should conform to data, and then should balance between conformity to data and parsimony. That means be simple but not so simple. Then it should be easily generalizable. Easily generalizable. It should not be difficult to generalize, because I was saying the other time that a model is a caricature of reality. You have a real situation. You want to simplify it, but not so simple, to the point that you are leaving the detailed features completely off, because you want to simplify it. So, but you have made it so simple that like Orapo, you bought Coca-Cola and say, man, they should have, or maybe you give it to your daughter self. Where mama and sugar. You put water until the Coca-Cola become water. You understand? Mommy, but this one is even water now. Alright, so some models are like that. Because you want to make it so simple and very simple, you are trying to remove the details. And then the model becomes useless. Now, validate model and make predictions. Now, people are doing validation, but less people are doing predictions. You see people, you just do the call and then say, my model fit in the data, but where is the prediction? So we need to draw a line. Now, I'm not going to this. So I will move to, I needed to build that background alongside what you have been doing since yesterday, so that we'll be able to understand what I want to teach further this morning. Now, I hope the people online are seeing this. Now, basics on our software and all that. We have started yesterday. We have done some simple stuff and all of that. So, I've explained something on R yesterday in terms of the programming, the environment for statistical computing and graphics. And it is highly versatile, extendable, computable. R is free to use. It's strong. It has a strong ethic in the community of free and open source material. And then it is reproducible, makes error detection easier and eases the workload and community of users. These enormous. You know, we have different kind of platform now. We have how ladies. You go to Twitter, you see how ladies there, and join. You know, you are put on. You go to your Twitter, just type how ladies, you see them. How ladies, how ladies, ladies, how ladies. It's a group. They put different kind of function every week. I'm part of them. Yes. And you see now, the issue is promoting women. You know, like most of the time, in our culture, We have put women under bondage. I'm sorry to say. Yes. I read the Bible, and one day some people they brought one woman. She was having an affair with a man. In fact, they brought him to Jesus. They said we caught this woman in the act when she was doing it. Now the question was, where was the man? It takes two to tango with them. They didn't bring the man. So Jesus started writing on the. So when he wrote it, he said, if there's any one of you that have not done what this man has done, woman, you can throw her his food. And that was how everybody left. All the people who wanted to accuse him, they left after that. They left. And when they left, Jesus said, I have not condemned you. Have mercy on you. Go and sin no more. So we're in a generation where you put women down. Are you getting now? And people are trying to change. We are not saying women should be the head. Woman is not the head, the woman is not the head, but give the woman a chance. Let him live, let her live a purposeful life. You know, like I used to say that, you know, some people who have that understanding, when you build a woman, you are building your life. Because the issue is that when you are at home, on the way, ọwọ́ méjì la fi ṣọwọ́ understand. So when a woman supports you, if you gain a woman support, you can get to anywhere in your life. So you need to support the woman for a woman to support you. Yes, it's like a stool. You have a stool. If you don't have, for you to construct a stool in your home, and if you make a woman a stool, it will shoot you up. That means you make her high. Once you make her high, you be high. You don't know? That's the story. If you make a woman high, take your wife here. Now, if you want to climb to that place, you just need to mount on her and get there. So, if you take your woman to that roof, you want to get a higher roof, just like you want to take my husband, just come. And you go. You stand on her, and then you get to the place. That's what so many men don't understand. God will give you understanding. Functions. A function is a code operation that has set inputs and return a transform output. You know, yesterday, we were trying to do something yesterday. I wrote the function f, and that function is a function of x, right? And it was 1/2 pi. That means, sorry, I don't want to write it, so let me just write 2 times pi multiplied by e raised to power minus x squared over 2, right? And then I close it. This is a function. So, okay, let me write it. Sorry. Okay, you see now, when you see that, you cannot see very far. So I will write it now. So I asked us to run this code. You know, this is a small function. And then I open it. I have 1/2 square root 2 multiplied by pi multiplied by exponential minus x up to all over 2, right? That was the function I had yesterday. So this function is like, I said, the function is a code operation that accepts inputs. So what is the input for this function? X. So I can say my x is equal to sequence minus 1 to 1 by 0.2. Can you run this one now? And let's see this function. Minus 1 to 1 by 0. That means it's going to give an interval of 0.2 difference. Minus 1 by 0.2 difference. So minus 0.8, I'm sorry, 0.6, 0.4, like that.
Ekiti State.
So when you do that, you now have, you can say that plot x comma f of x, then type equals to L, and then color equals to red, and then line width equals to 3. LWD. So for this, you are expected to get a bell-shaped structure, not a normal distribution, not the curve you had at that time. Now, we need to learn functions in order to write your own code. With this, I can write my own code. I don't need to see your code. Once you give me what your problem, once you learn how to write functions, you can write any code anywhere. Which one? This one? No. LWD equals to 3. So it's the length of your line is that, so it becomes brighter. Did you get ends like this?
Yes.
No.
Yes.
No. Okay. Can you try
Minus 5 to 5.
minus 10?
Sir, the x limit equals to
Okay. The limit of x, huh?
So it's minus 10 to 10. It's correct that way.
You can say maybe to 0.1. Try it, let's see. Okay, that's fine. The
sequence of
you get it? Yes. You are supposed to get the friendship. So, I want to give you an assignment. Not detailed. The part you're going to present to me. What you say, take home one. So you build a function and then you plot it. And you bring in the plot tomorrow. Yes. norm of C minus 10 to 10. Can you try it? C norm of this. Right? You get the same. So because like what I did, I use the formula. That formula is packaged inside this in how by default. So this function. So once you use this thing, it will give you. So is normal distribution supposed to be like that? That's the way. But there are some lambda cap of t. So lambda cap of t is equal to 0. If t is less than tau, then is equal to a over 1.5. If t minus bracket t minus tau, if t tau less than tau plus 1.5. And then this is a bracket tau plus mu minus tau all over mu minus 1.5. If tau plus 1.5 is less than or equal to t less than t plus tau plus mu, and then 0 if tau plus mu less than t. So plot lambda of t. Plot lambda of t. That's the assignment. It's part of your thing you present tomorrow. So T must appear like this. Lambda cap. So now lambda of t is 0. If t is less than tau, this is tau, less than tau. No, this is the whole of t. So at this place is 0. So when t is greater than tau, but less than tau plus 1.5, you have this. That's like you are having what's it called? Half base times height. You know what it means? Half base times height. And then tau plus mu, minus t, minus 1.5. If tau plus 1.5 is less or equal to t, less than tau plus 10 from mu. And then 0 at this point. It is 0 at this point. So if tau plus mu is less than t, so you provide this graph for me as part of your presentation. Even this code. So that's a 1 point. A times tau and a t right number. Yeah. Okay, maybe I should give the value of tau. Okay, t can be from 0 to 20 by 0.5. Just to give you another clue. So you must come up with this kind of graph. So can we move forward?
That's one of my Sir, are we the ones to determine the values of eta and tau?
Of the tau.
And eta.
Okay, let me give you the value of tau. Only tau. For chi, you have it.
And eta.
I'll give you the value of eta. Tau is equal to 2.5. Tau is 2.5 and mu is 13. Mu is 13. Tau is 2.5, mu is 13. So, RStudio is a graphical user interface. GUI for easier use. And then you have the objects. Now everything you store in R, like your data sets, the variables, a list of village names, a total population number, even output such as graph, they are all objects. And then which are assigned a name and can be referenced in later commands. And I'm talking about functions. Now, we want to look at trajectory matching, prevalence and incidence. Now, when we fit mechanistic models to data, you have to consider carefully the relationship between the nature of the data versus the nature of the model state variables. Now, what do we mean? Now, there are different types of data we can have. The data can be a mortality data, that is that capture the death rates due to the disease, and then we can have prevalence data, which has to do with what is prevalence. If I will ask, prevalence is somebody want to tell me, is the total number of both old and new cases of disease. Let's take for instance malaria. The total number of both old cases of malaria and new cases of malaria. That's prevalence. Prevalence over a period of time. So prevalence majorly are cross-sectional, maybe within a particular short period of time. But incidence is what? What is incidence? Incidence is the number of new cases of disease. Now it may not only be disease, it may be new cases of anything. Incidents can be new cases of everything. But in terms of disease, is the new cases of number of new cases of disease within a period of time. Now, when you look at incidence and prevalence, they have some relationship, but they are not the same. And then we also have cumulative incidence. Cumulative incidence is, like you have cases of, let's take for instance, we are capturing Lassa fever. You have cases, a case today, and yesterday, one case, and today you have 3 cases. Now, what is now cumulative is 1 plus 3 is 4. And then you add 1 of next, 4 plus 4, 8. and then you are adding. That's cumulative, just like the OGIF. So cumulative is, so in the long run, the cumulative, when you now draw the blocks, it's going to be a straight line. And that's what so many people are working on. They said they are model, and then they model the cumulative, and then they draw a straight line. They said they are fitted. That's not a good fit. Only fits cumulative. Now within one or two cumulative, there are so many cases that you have left behind. So in other words, if you have a cumulative data, you can extract an incidence data from a cumulative data. What do you do? XN minus X naught. So I mean subtract the previous from the recent, and then you have it from like that. And that's what we are going to do here now. So you can always get extract one from the other if you don't have. Now, we therefore start now. So for example, when we work with continuous time SIR or SEIR models, it is important to keep in mind that incidence is not prevalence. It's not. So if our data is incidence, we will need to do something more than trying to match simulated prevalence. Are you getting that? So, for example, when we work with continuous data, it is important to keep in mind that incidence is not prevalence. It's not. They are not the same. So, if our data is incidence, we need to do something more than trying to match the simulated prevalence with observed incidence. So, we therefore play with a toy example using simulated data. So, if you can assume that the dynamics is unaffected by process noise. Process noise are like demographic and the environmental capacity. You can feed models to data using trajectory matching. So one of the best ways we advise is that if you are going to use model with the data, the first thing you do is to first of all do the trajectory matching before you finally fit. So that you will know the shape, whether the shape of your data is in line with the shape of the model. Now, if you establish that, it will also give you an understanding of the base parameter you are going to use for your fitting. Take for instance, you have the data. I'm going to clean this one up. You have the data, and you have matched your model with the data, and the data is like this or something like that, and then your model is able to capture it and as in represent it. When you have not fitted, you have not done any fitting. Now you want to fit some parameters, maybe like natural ability or something in the data, and you have used a particular parameter value here. Keep that parameter value. And you could use that parameter value when you want to fit. Since you have seen that the shape that your graph is giving is the same as the one. I'm going to started. So already when you have done the matching, you can see that there is a match to your data and your model. Now, there are parameter values you have used to get this. Now note that also that when you are modeling and you are using the data, there is a particular unit of dimension that your data calculates. Now if you are getting the data that is monthly data, if it's monthly data, it means that your parameter values in the model should be converted to per month. Because your data is what? It's monthly data. Now if your data is weekly, it means that the parameter values you are using should be per week. Now, if your data is per day, is taken daily, it means that your parameter values in the model should be per day. Now, once there is a disruption between these two, then you find out that you are having trouble with fitting. The model to data. And you see that this aspect is one of the most important aspects when it comes to policy making. want to start doing modeling that is policy driven, you have to learn this very well. Not just model and then you are schooling around and then you just do all the theory, you do all the lab and all of that. It's good for maths. That is maths stuff, like that doesn't have the formula. And you get to say now, you do that, you are happy. So you can do that for maths. But if you want to speak to public health officials, you don't need that enough. What do they want to use it for? Global stability, you don't need it. All you need is learn how to develop your model, do a schematic diagram, do the model, and do the quantitative analysis of the model in terms of finding the outcomes, getting to use your data with the model, and then predict. Let's see how your form goes, and let's see what happened in the long run. Let's say the model is telling us that within a particular confidence interval or predictive interval, there's going to be like 150,000 cases of malaria. Then everybody will begin to wait that, let me tell you something. In the present day world, people are looking for prediction. What will happen tomorrow? Even the government, they want to see. Because they want to see what they are spending money on, what will bring the evolution. Yes, I'm going to spend money, $1 billion. So if I spend $1 billion, what will be the evolution over time? So if the guy can see that within a particular time confidence interval, they are giving him, the guy is confident and say, okay, it means that this thing is going to work. So let's go into it. And you get it now. So everybody needs that. So in doing that, we can fit models that are using trajectory matching. The assumption is that discrepancy between the observations and prediction from dynamics model are due to observational errors. Now there's there's no data that can be too perfect. In the course of collecting data, there will be some errors, noise, and all of that, which can bring about some discrepancy, little ones, between the models and data. You understand? And that is why we come up with confidence intervals. That within this particular, you see now, we were traveling to Abuja one day, and then with my students, and the flight was by prediction, it was to arrive in Abuja maybe by 11:30. That's prediction. But that was, they would tell you there that there is a particular word they use, their proposed time or something like that. So they have done some models to come up with that time. But do you know that we took off the same time, I think the same time that was allotted for that flight, but we got to that place 15 minutes before. So the guys sitting beside me now asked me, why is it that they said 11:30 and we got to 11:15? I said there's a confidence interval.
Alright, so we will continue after